So such multi-scale atomistic modeling of magnetic tunnel junctions, MTJs in MRAM, with ab initio DFT methodology and atomistic spin dynamics, plays an important role in the continued scaling and performance improvement of memory devices. It enables R&D engineers and researchers to do both, to consider the performance of novel materials, thin layers, and interfaces in MTJs with little experimental knowledge. And at the same time, it enables to take into account realistic dimensions, size, temperature, and dynamic effects on MTJ spintronic properties using atomistic spin dynamics. And here is today's webinar outline. Our invited speaker, Dr. Richard Evans, will start with introducing atomistic spin dynamics, Vampire software capabilities, and present application examples for MRAM modeling. Then my colleague, Dr. Troels Markussen, will take over and discuss why to use ab initio parameters in Vampire, demo Vampire integration into QuantumATK NanoLab GUI, and present an application example of such QuantumATK Vampire multiscale atomistic modeling workflow. And in the end of today's webinar, we will have our Q&A session.
Okay, so today we're looking at magnetoresistive random access memory, or MRAM for short. I'll talk a little bit about some fundamental properties, about how we can model those, and then also moving on to dynamics and how these individual devices switch essentially, and what's the kind of the properties of that particular device. So one of the things you can do with atomistic models, because you have temperature effects involved naturally, you can do temperature-dependent hysteresis loops, which allows you to look at how the system responds to an external field, but also how the fundamental properties like coercivity change as a function of device size and temperature, and of course field weight. So here what we did was we looked at a relatively small device, I think around 10 or 15 nanometers in diameter, and then looked at the temperature dependence of the hysteresis properties, showing how the coercivity both decreases with temperature. So you can see that for 5 Kelvin, for 10 nanometers device, with 5 Kelvin, you have a very large coercivity, around about 1.4 Tesla, so it's much larger than actually you see in experiment, interestingly. I'll come back to that a bit later. But the coercivity is large, but then when you add thermal fluctuations, this drops a huge amount down to around 0.25 Tesla on average. And so the reason for this drop is A, that the fundamental anisotropy changes with temperature, but also because the device is very small, the thermal fluctuations are relative to the volume very large, and that gives you a extra decrease in the coercivity compared to what you would expect, just from the scaling of the fundamental properties. So this is where atomistic models really become useful, because you get extra physics in terms of finite size effects that you can't necessarily do from analytical theory very easily. So here you can kind of compare how the reversal mechanisms now change. So again, this is a hysteresis loop, and we're looking at a snapshot of the magnetization. So here, blue in this case is the up magnetization. Then we apply a reversing field, which will try and turn the dots red. And we now compare that for a small device, around 10 nanometers in size, and a large device, around 50 nanometers in size. And then also at comparing 5 Kelvin, which is low temperature behavior, and then 300 Kelvin, which is, if you like, room temperature-ish behavior. You can see immediately there's fluctuations in the 300 Kelvin devices, but also that the reversal mechanisms are different. So here the device tends to switch by nucleation and propagation mechanism at a higher temperature, whereas at low temperatures, the reversal is more or less coherent for the small devices. We also investigated spin transfer torque dynamics. So this is then having a bilayer simulation. So we have a reference layer and a free layer with an NGO barrier in between. And then we apply spin transfer torque switching to see how different devices of different sizes and temperatures switch in this STT effect. So here what we have is we apply current through the device. And so we're actually going from the anti-parallel configuration to the parallel. And what we're showing here is that the dynamics of the devices are slightly different depending on the size. So at 20 nanometers, it's more or less coherent, which means that all the spins tend to lie the same way. So you get the length of magnetization is essentially constant through the switching process. So here, what happens is after around some waiting time of around half a nanosecond, you need to sort of start the procession going, and it's very, very tiny to start with. So you have this reversing polarization, and this then gives you an increase in the procession as you go through, and then a coherent switching of the device. With 30 nanometers, what you see is slightly different. You see a transient drop in the magnetization length, and that's due to forming a partial domain wall in the system during the switching. So again, here the finite size effects begin to matter, and you induce a slightly different reversal mechanism based on that.
So why do we need ab initio input to spin dynamics simulations in Vampire? So there can be several reasons. First reason is if we consider iron and cobalt as are the typical ferromagnetic materials, they have rather long-range exchange interactions. And it is not a priori given that all effects will be well represented by a nearest neighbor model. So this could, for instance, be the exchange stiffness that depends critically on the distance dependence. Another reason is that when we consider a structure of an STT-MRAM stack indicated to the right here, it's evident that there are lots of interfaces and lots of thin layers. And close to interfaces, several magnetic properties become different than they are in their bulk environment. This is true for the magnetic moment, exchange constants, magnetic anisotropy energy, DMI vectors, if they would be included, and also spin transfer and spin orbit torque occurs close to interfaces. So let me just give a brief example of one of these. So here I am plotting the exchange interaction Jij between iron atoms, and I start out by showing the results for bulk iron. So this shows the exchange interaction between different iron atoms as a function of distance. This is calculated for a bulk BCC iron crystal. If I now calculate the exchange constants for this iron layer surrounded by MgO, I start out by looking at a central iron atom. And in this case, I get more or less the same distance dependence for the exchange couplings as for bulk. So in this case, the results are similar and a bulk model could be applied. However, if I instead consider the interface as iron atom here, we notice that it has a very different behavior for the exchange interactions. Close to the nearest neighbor, it's almost double the size of the exchange, but then there is a large antiferromagnetic coupling to the second nearest neighbor, and in general it is quite different. Also notice that the magnetic moment for the interface atom is 2.76, whereas in bulk and in the middle of the slab it is 2.3. In addition to the effect of interfaces, another motivation for using DFT or ab initio input could be that if we are modeling new materials or material combinations with little experimental knowledge.